All right, I'm going to give this another try on recording our lecture for today for properties of gases. So this is part one of three parts, and here what we're looking at is being able to identify methods of how to measure atmospheric pressure. We'll also talk about Avogadro's law and density of several gases. So this is a big point here on this slide. First off, it's to understand really what pressure is. Ooh. Okay, resume slideshow. Okay. So first off, it's to explain what pressure is, and these are the different pressure measurements that we'll be using in respiratory care. Pressure is defined as force per unit area, expressed, for example, in grams per square centimeter or pounds per square inch. So this PSI measurement, this is the measurement that you'll measure the tire pressure in maybe your bicycle or your automobile. For gases, pressure is directly dependent on the system temperature because of that effect on kinetic energy and on the gravitational attraction of the Earth. The force exerted by gases is greatest at the Earth's surface and decreases with altitude. In fact, in spite of a constant oxygen concentration up to an altitude of about 50 miles, the density of the atmosphere markedly decreases, as does the total force exerted by the atmosphere and its component gases as altitude increases. So really think about it. If we look at this picture here, we see the amount of atmosphere pushing down on this sphere of mercury in this example, but as we go up in altitude, there's less to push down on that gas. Gas pressure is frequently expressed as the height of a column of fluid. Most of the time we're going to use either water or mercury. The use of these expressions is based on the principle that the barometric pressure, so again that's big P, little b, is expressed to the height of a column of fluid housed in a vacuum when exposed to atmospheric pressure multiplied by whatever that fluid's density is. So if we see here, if we compare centimeters of water to millimeters of mercury, gas is 13 times less dense than water. So again, and then mercury is much denser also than mercury is more dense, than water. So the way we measure these is based on the density of the fluid that's being used. So when we do these conversions, so pressure expressed in millimeters can be converted to true pressure by multiplying it by the density of mercury. The pressure exerted by an individual gas in a mixture is referred to the partial pressure of the gas. So that's where we talk about PO2, partial pressure of oxygen, or PCO2, partial pressure of carbon dioxide, and is usually expressed again in this millimeters of mercury. So we've worked with these before. 760 torr is the average barometric pressure at sea level. Torr is interchangeably changed out with millimeters of mercury. And then another measurement commonly used in respiratory care is centimeters of water pressure. And occasionally we'll do calculations at 1 ATM or expressions of an ATM. So quick review. Here is a few calculations that you could do by using those conversion factors we were just talking about. So pressure again is equal to the height times the density of the fluid. and try converting these different expressions in the units. So what about Avogadro's law? Avogadro's law states that 1 gram of any substance contains exactly the same number of atoms, molecules, or ions. So volumes of gas under the same condition must contain the same number of molecules. So 1 mole of a gas at a constant temperature and pressure should occupy the same space as any other gas. So this number then is 6.023 times 10 to the 23rd, and that's what's considered Avogadro's constant. So when we calculate that out, what we find is at standard temperature and pressure, so at 0 degrees Celsius and at 760 torr, the molar volume of a gas is 22.4 liters. In reality, there are some, in reality, there's a few variations depending on the physical and chemical properties of a given gas. So, for instance, CO2, the number actually comes out to 22.31. So what about density? We use Avogadro's law to calculate the density of substances. So given that constant molar volume of 22.4, how do we calculate density? Density, in and of itself, a dense substance has a heavier or higher atomic weight, meaning the particles are packed closer together. So density is a ratio of mass to volume. Density equals mass over volume, and that's how we calculate density. So if we look at this in an equation, density equals mass over volume. In clinical practice, the weight is actually substituted, or the weight is substituted for the mass. So we use gram molecular weight. If you'll look on page 105, if you have the 9th version of Egan, or 115 if you have the newer version of Egan, you can see some of these conversion factors to walk through this. So how do we find the gram molecular weight of oxygen? Well, we look at this lovely periodic table that you all remember. So here we have O. O is equal to 16 for the gram molecular weight. If we have O2, we're going to take 16 plus 16 is equals 32. We're going to take 32 and divide it by 22.4. Again, 22.4 is that given constant molar volume that we got from Avogadro's law. And if we calculate out 32 divided by 22.4, we would get the density weight of oxygen being 1.43 grams per liter. So now what I want you to do is look at the density of other gases. So calculate the density for nitrogen, helium, and carbon dioxide on your own, and refer to your text if you have questions.